Hi, good day all of you. Welcome to our session. Welcome to our channel, Intelligible Tutorials. In this today's session now, I want to give the clear introduction of the new kind of the knowledge representation. Those are called as slot and filler structures. Okay, what is the meaning of the slot and filler structures? First we see here. So, the slot is nothing but the attribute and the value of that particular attribute is called as the filler. So this is the exact definition of the slot filler structure. Okay, so slot is means what? Attribute and its value is called as the filler. And again, the slot filler structures are divided into two types. One is weak slot filler structure, another one is the strong slot filler structure. And for this weak slot and filler structures, we are having two different kinds of the things. Those are semantic nets, two kinds of the representations of weak slot filler structures. Those are semantic nets, frames. And coming to the strong slot filler structures, we are having the conceptual dependency and as well as the scripts. The first one, we are giving the introduction of the weak slot filler structures. So why the name is given as the weak slot and filler structures? Okay. Normally, the name weak represents the poor knowledge, or very little importance is given to the knowledge or the structure that should have. Whereas the strong slot filler structure is the strong knowledge and very high importance is given to the specific knowledge how it is going to be represented. So that's why high representation of the specific knowledge that is there in the strong slot filler structures. Whereas in the weak slot filler structures, the knowledge representation is very poor and very simple kind of the knowledge or the very simple kind of the knowledge, the structure of the knowledge that can be represented in the weak slot and filler structures. The basic things for these weak slot filler structures, the basic representations are semantic nets and as well as the frames. And coming to these strong slot filler structures, we are having conceptual dependency and as well as the scripts. So this one is the introduction of the slot and filler structures. Now we see what is the meaning of weak slot filler structures. Okay, I told previously the poor knowledge and of the poor knowledge structure that it can be represented. And one more thing related to this weak start pillar structure, it can represent only the static representation of the things and as well as the structural relationships can be represented by using these weak slot and filler structures. And no hard and fast rules, no dynamic rules are introduced in the weak slot and filler structures. Okay, weak means what is the meaning of this weak actually? The poor knowledge relationship. It is completely static, not dynamic relationships, only the structural relationships and poor knowledge can be represented. The best examples for this are semantic nets and as well as the frames. Okay, now see what is the advantage of this actually the total slot filler structures. Why we go for these slot filler structures? Okay, what is the two kinds of the reasoning, monotonic reasoning and non-monotonic reasoning? Here the monotonic reasoning can be performed more effectively using the weak slot filler structures. With pure logic and non-monotonic reasoning is easily supported. Okay, so we can represent monotonic, we can represent non-monotonic reasoning. Okay, monotonic reasoning can be performed more effectively than with the pure logic and non-monotonic reasoning is easily supported. Mono means one, only one value can be represented, the truth validity of a statement. Non-monotonic reasoning is comes under the uncertainty, the logical validity of the statement is completely uncertainty, we can't predict exactly what it is. That is called the non-monotonic reasoning. All the uncertainty things whatever we are having comes under this non-monotonic reasoning. Okay, so it makes it easy to describe the properties of the relations. It makes very easy to describe the properties of the relations. Does oven has part called nose or not? Okay, so like this it represents such kind of the relationships, yes or no. Okay, true or false, like that. Next, form of object-oriented programming and has advantages such as modularity in days of viewing by the people. These slot filler structures can also be represented by using the object-oriented programming and also having the advantages like modularity and ease of viewing by the people. It also represents the modularity and it also one form of the object-oriented programming. Okay. So next we are talking about the one kind of weak slot filler structures, that is semantic nets. What is the meaning of the semantic nets? Semantic nets, the information can be represented as set of nodes connected to each other and with the set of labeled arcs like this. These are the set of nodes and these are connected like this. Nodes are nothing but various objects and values of the objects. Arcs are some kind of the relationships among the objects. For example, Jack is a person. He is the instance of the person, and this person is a mammal. So, is a and instance relationships are clearly representing here. And person has a part, knows. Has part relationship also representing here. And Jack is that is the uniform color of the Jack is blue, and the team of the Jack is Chicago Royals. Like that, the name of the relationship is also clearly specified, and the each and every object can be represented like this. Okay, so these are the relationships among the nodes. This is one best example of the semantic nets, which can be represented as is a part, has a part, instance of relationship, and the uniform color team, like that. Some another names also we can represent in the semantic nets. The next one, in this network we could also use inheritance to derive the addition has part Jack note. Okay, some kind of the inheritance also we are representing like is a has part like that. Okay, so next one, coming to the intersection search. What is the meaning of the intersection search? One way to find the relationships. It is nothing but one way to find the relationships among the objects to spread the links out from new nodes to find out where it meets. First of all, the best example we take for this intersection search in this given diagram is the relation between the red and Liverpool. What is the relation between the red and Liverpool? Okay, this red and Liverpool, what is the relationship? We are obtaining such kind of the relationships among the objects by using some set of the links is called as the intersection search. Okay, so, mum oven is the person, is the instance. Okay, so next person is a mammal. Oven is the instance. Next, this oven, a uniform color, and team is nothing but Liverpool. So, what is the relationship between the red and Liverpool? Red and Liverpool are the two different kinds of the values of the attributes for the uniform color and as well as the team of the oven instance. Okay, so that kind of the relationship if you find in a given diagram, then that is called as the intersection relationship. So red and uniform color are the values of the attributes as uniform color and as well as the team of the instance oven. So we are finding the relationship of such kind of the attributes and the attribute values is nothing but the intersection search. Okay, so we can find this intersection search also in the semantic nets. And next one, representing non-binary predicates. Okay, so here we are going to see unary. Example, man of Marcus can be converted into instance Marcus of a man. So Marcus is the instance of the man. Other are it is score India Australia 4 comma 1. Three or more predicates can be converted to binary form as follows. Create new object represent the entire predicate. Introduce binary predicates to describe the relation to this new object. Okay, so how can we represent these non-binary predicates? Unary, binary. Unary means man of Marcus. Okay, so man of Marcus is one example of this one, and the binary is instance of man, instance of Marcus, comma man, and other kind of the things are score India, Australia 4 to 1, and other kind of the predicates converted into the binary form as the follows. We can convert them into the other form of the binary forms. We can create new object representing entire predicate and introducing the binary predicates to describe the relation to this new object. Okay, so these are the examples of some binary predicates and as well as non-binary predicates. Okay, So now we take one. Unary means it holds only one value, binary means it holds only two different values, and other means it can hold three different kinds of the values. Okay. So next, score India Australia 4-1. How to represent this in the using the semantic net? We will discuss some of the examples of the semantic net. Okay. Australia, India, two different nodes. So there is a test called test 4. Visiting team is the Australia, home team is the India, and test score is 4-1. And what is the test? The test is actually a game. Okay, like that, the entire statement, the entire thing, predicate can be represented by using the semantic net like this. See, what is the hosting home team? Is the India, and Australia is the visiting team for the test 4. Actually, test 4 is what? A game. And what is the score here for this? 4-1. Okay, so like this you can represent the predicate in the form of the semantic net. One more example we see based on this. John gave the book to Mary. This is converted into the predicate form like give John Mary book. Okay, for this we are using some auxiliary objects here. These are the intermediate objects or the auxiliary objects that we are taking the help of this to represent the relationships. Mary, John, and book and give. Okay, so Mary is the beneficiary who is taking the book, and John is the agent, giving the book. Okay, so John giving the book, this can be represented, give can be represented as EV1, and book is represented as BK1, where EV1 is the instance of give and BK1 is the instance of book. Okay, so these two are some auxiliary objects or necessary objects that we can take the help to represent this give and book. We can't represent this give and book directly here. With the help of these auxiliary objects, you can represent this give and book. So Mary is connected to the EV1 give instance. She is the beneficiary, and book is the BK1 is the instance of the book, and John is the agent who is giving the book. So this kind of the predicates can be represented by using with the help of these two auxiliary objects. Okay, the next one, making some important distinctions. Some other examples. John has height 72. John height 72. Okay, and John is taller than Bill. How can we represent this? John, Bill. First of all, we can take two John, Bill. Height, for height we can represent this one as the h1, and bill height is less is represented as the h2. H1 is greater than h2. Okay, instead of representing John is taller than Bill taller than Bill, which one is which property you are representing here? John is taller than Bill means what? In the height you are saying. So for that height you are creating two different kind of the auxiliary objects here. Okay, secondary objects, these are h1 and h2 greater than h1 greater than h2. Okay, so what is the value of the John here? H1 is 72. Okay, so H1 is greater than H2. Like that, you can represent this kind of the relationships like this. And we can partition the semantic nets also. How can we partition the semantic nets? These are used to represent the quantified expressions in semantic nets. One way to do this is to partition. We can represent the partitioning the entire semantic net into some kind of the hierarchical set of these places, and which corresponds to the scope of one or more variable. Okay, so the partitioning of a semantic net can give more clear meaning. This is used to represent the quantified expressions. What are the quantified expressions? How they clear give me, how they can give the clear meaning. Now we are going to see. Let us have the very good example, that is the dog bit the mail carrier. Okay, dogs bite mail carrier. Three objects I have created. Let's see carefully. The statement is the dog bit the mail carrier. Dog bite mail carrier. Okay, so for the dog I have created another object, that is D. D is a dog. Okay, and bite, it is a verb actually, bite. For B I have created bite, I have created B, and mail carrier M. Okay, so what this mail carrier actually, it's a victim of biting of the assailant by dog. Okay, and what is the relationship for this D, B, M to the respective objects? D is a dog. B is a byte, and M is a mail carrier. Instead of representing these kind of the relationships into the directly to the existing objects, you can create some help of these auxiliary objects, and from them you can represent these relationships. So M is the victim by the salient dog. It is bitten by dog. Okay, so the dog bit the mail carrier, you can represent like this. For this the partition is not required. How this can be partitioned in the coming one, now we see how it is partitioned. These are the partitioned things. See here, every dog has bitten male carrier. Some other kind of the representations we use it here. How it is now we see. Let us see before going to this partitioned semantic net. See, this is the inner semantic net. This one is the inner semantic net. S1 is the inner semantic net, and SA is the outer semantic net. Okay, so for this, we are going to see this example, that is every dog has bitten a male carrier. For all x, dog of x2, their existence y, male carrier of y, and bite of x comma y. How to represent these universal and existential quantifiers? In the statement, we are having universal quantifier for all x and their existence y. Okay, how can we represent these two? Okay, so let node G stands for assertion given above. This node is an instance of the special class GS general statement. Every general statement has two attributes, that is form, and second one is the for all connections. SA is the space partitioned in the semantic net. Okay, so see here, there is a general statement. This one is the general statement. For this general statement, G is the instance. G is a general statement. This general statement is representing form and for all. Okay, form is representing to this partition net, and as well as this one is the for all. And what is this SA? Sorry, what is this SA? This SA is the space partitioned in the semantic net. Okay, so what is the S1? S1 is the space for the objects, auxiliary objects for what we have created. So every dog has bitten male carrier. Here we are having the for all x. For all x can be represented by using the GS. GS is having another object called G. So G is the GS. So this is applicable to whom? Every dog has bitten the male carrier. So this general statement is connected to dog because every dog, but not every male carrier, only dog, every dog. So it is connected to the dog D object and as well as the entire spare partitioned semantic net. So SA is the partitioned whole part of the semantic net, and S1 is the auxiliary object partitioned. Let us see as per in the previous example what I showed, the same thing here also existing. That is, the dog is having D. D is the represents a object of dog. Is a D is a dog, and B is a bite, and M is a male carrier, and M is a victim, and B is the salient S1. So this is the partition of the S1. Okay, for this partition for all is applicable, so that's why I applied GS to this, G to this, this object to this entire, this one entire S1. Okay, so you can represent the partitioned thing like this. One more example, every dog in the town has bitten the constable. Every dog in the town has bitten the constable. Again, you are having every means for all. So that's why you are using GS, general statement, and G is the object of it. G is a general statement. Form of dog. Every dog in the town. So again, it is representing to what? D only. D and this particular partition net. In the same as previous, SA is the whole semantic net. In that partitioned one is the S1. So D, and D is a dog, and B is a bite, and constable is the M. So in the previous case we have represented it as male carrier, but here we are representing is the constable. So what it is representing now, see. So M is the victim and B is the salient. So what is the S1 here? It is partitioned up to the this one only, up to this one. Okay, D and B only. Every dog in the town has bitten the constable. This general statement can be connected to dog has bitten the constable in the town. Okay, so this is the partitioned S1. Like this, it can be represented. Okay, so this one is the example of every dog in the town has bitten the constable. Now see, we see another example. Every dog has, this one is the one example, and now I am changing, this one is the another example. Every dog in the town has bitten every constable. Every constable. In the previous case we have only every dog has bitten the constable. Now here we are having every dog in the town has bitten every constable. So this is the for all x dog of x, for all constable c of x, like that we can represent. So general statement can be applicable to dogs and as well as the constables both, and the partition net also s1. Okay, so for all can be applicable to what? Here general statement is nothing but for all. It can be represented to, it can be applicable to dog, every dog, and as well as every constable. So for all can be applicable to dog, and for all can be applicable to constable also. So let us see how it can be represented. This is the whole semantic net SA, and in that the partition one is the S1. Dogs D is a dog, B is a bite and constable, and C is victim assailant. Okay, so for all can be applicable to whom here? For all can be applicable to D and as well as the constable here in this particular example. Like that, you can represent the for all relationships, for all quantifiers by using the general statement GS in the respective examples. Okay, so this one is the example how to represent the for all. Now see another example of the semantic net. Okay, Mary gave the green flowered vase to her favorite cousin. Mary, cousin, green flowered. Okay, cousin is the beneficiary. In the same manner, John gave a book like that. Here also, I am taking the help of some auxiliary object, that is EV1, that is connected to G1. So cousin is the beneficiary. Mary, who is giving, is the agent, and Mary. mm to Mary and cousin is the favorite. What is the relationship between the Mary and cousin? Favorite cousin. It is. She is. And vase. And who? What it is giving? Green flowered vase. So vase. What is the colored pattern of this vase? Green flowered. Okay. So she is the agent. Give instance to the vase. What kind of the vase it is? Green flowered vase. To whom? Who is the beneficiary? Cousin. Like that. You can represent the semantic nets like this. Some more examples also we can see based on the semantic nets. Every batsman hits a ball. For all batsmen hits a ball. Here also you have to use the general statement. General statement can be represented as small g is a form for all. Okay, so batsman, b is a batsman, h is a hits, b balls, and the partition net is s1 and whole is the sa here. So what the actions can be, how the actions can be represented. So hits a ball, it acts on. So batsman giving some action, what kind of the action? Hits. So what kind of the action on B? Acts on, hits. Okay, so for this what this for all is represented to what? For all statement, general statement is connected to whom? Every batsman. So it is directly connected to B object and the entire whole S1 partition. Okay, so like this, whenever you use for all, you have to take care of this kind of the partition nets. Okay, so general statement is one of the important one. You have to remember whenever you are using the quantifiers like for all, etc. Okay, so next we see another kind of example. Tweety is a kind of bird who can fly. It is yellow in color and has wings. So how can I represent this? Tweety is the instance of a bird, has part wings. So bird color is yellow and bird action is fly. You can represent the entire statement in the form of semantic net like this. Bird instance is Tweety, bird has part wings, bird color is yellow and bird action is fly, like this. And some more examples of the semantic nets. Let us see. Tom is a cat. Cat. Tom is a cat. Tom caught a bird. Tom caught a bird. Tom is owned by John. So Tom owned by John. Tom is ginger in color. Is colored ginger. Cat likes cream. Cat like cream. The cat sat on a mat. Okay, the cat sat on a mat. And the cat is a mammal. Cat is a mammal. And bird is an animal. Bird is a animal, and mammal is also an animal. All mammals are animals, so mammal come to this animal. Mammals have fur. Mammal has fur. So entire set of the statements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 number of the statements are there. They can be represented by using the 10 number of the objects and their relationships using this. It's a very good example of the semantic net. How the objects can be represented and their relationships can be represented. So this is about the semantic nets of the weak slot filler structures. Okay, so this is the one of the best example. Semantic net is one of the best example of weak slot filler structures. In the coming video, we talk about the another weak slot filler structure, that is nothing but the frames. Okay, so please, if you like this video, please watch and share and like this video. And if at all you didn't subscribe my channel, please subscribe my channel, Intelligible Tutorials. Thank you one and all.